Welcome to the deep dive. Today, we're looking at something pretty extraordinary. Something that sounds like science fiction, really.
Yep.
An artificial sun built right here on Earth.
It definitely captures the imagination.
For decades, fusion energy has been this sort of holy grail, hasn't it? Clean, almost limitless power, but always just over the horizon.
The challenges have been immense.
Exactly. Like, how do you even create temperatures hotter than the sun? And then, maybe even harder, how do you hold on to that super hot stuff, the plasma, long enough to actually get energy out?
It's a monumental physics and engineering problem.
It really is. The Everest of energy research, you could say.
Right.
Which brings us to this recent news from China's EAST project, the Experimental Advanced Superconducting Tokamak. Quite a mouthful.
EAST, yeah.
Okay, let's unpack this achievement. Our mission today is to figure out what this artificial sun really is, what it actually did, and why it's potentially such a massive deal for our energy future and for you listening.
Definitely worth digging into.
And hey, as we get started on this deep dive, please do remember to like, subscribe, hit that notification bell, you know the drill, so you don't miss what we explore next.
And check out the affiliate links if you find this useful.
Yes. And drop your topic ideas in the comments. We genuinely love hearing what you want us to tackle.
What's fascinating here is, well, it's not just the science, which is incredible, but the sheer excitement around it. This feels like a real marker in that global quest for sustainable energy.
It really does. So this term artificial sun, it's not just hype, right? It points to the actual goal, mimicking the sun's fusion process.
Precisely.
Could you maybe give us a quick refresher or maybe a slightly deeper take for those who follow this stuff on what nuclear fusion actually involves and how these tokamak things work?
Sure. So at its core, nuclear fusion, and many listeners will know this, is about forcing light atomic nuclei together, usually hydrogen isotopes like deuterium and tritium.
Right.
Under immense heat and pressure, they fuse into a heavier nucleus, like helium, and release a huge amount of energy in the process. It's literally star power.
The sun's engine, basically.
Exactly. The challenge is creating those conditions here. That's where tokamaks come in. Think of a massive hollow donut.
Okay.
Inside that donut shape, you heat the hydrogen fuel until it becomes plasma. This incredibly hot, electrically charged gas, millions of degrees hot.
Hotter than the sun, even.
Much hotter in some cases, and obviously no material container can hold that.
It would just vaporize instantly.
Instantly. So tokamaks use incredibly powerful magnetic fields. They create a sort of invisible magnetic bottle, trapping and suspending the plasma so it doesn't touch the wall.
Magnetic cage.
A magnetic cage, yeah. Keeping it stable and confined long enough for fusion to happen.
And EAST, this Chinese project, is a special kind of tokamak.
Yes, EAST is significant. It's the world's first fully superconducting non-circular tokamak. That non-circular sort of D-shaped cross-section, that's key.
Why the D shape?
It allows for better plasma stability and confinement compared to older circular designs. It's just more efficient magnetically, which is crucial for running longer pulses of fusion.
And the superconducting part.
That refers to the magnets. Superconducting magnets, when cooled way down, have zero electrical resistance, meaning they can generate extremely strong magnetic fields very efficiently, using much less power once they're cold, and they can maintain those fields almost continuously. These design choices are what enabled EAST to push the boundaries.
Wow. So you're really building a tiny piece of a star contained by magnets inside this D-shaped machine.
If we connect this to the bigger picture, yes, that's precisely the goal. Recreating stellar conditions stably on Earth. And the challenge is just immense, reaching and holding temperatures far beyond the sun's core.
Okay, that engineering is just mind-boggling. Which leads us straight to the big news, the record itself. Here's where it gets really interesting. Our sources highlight two numbers, 17 minutes and 180 million degrees. Those numbers sound huge, obviously. But what do they mean in practical terms for fusion research? Why is 17 minutes such a breakthrough?
They are monumental. So EAST kept its high-temperature plasma going for 166 seconds. That's just over 17 minutes.
Okay.
And during that time, the electron temperature reached about 180 million degrees Fahrenheit.
Which is compared to the sun.
The sun's core is roughly 27 million degrees Fahrenheit. So yes, EAST was operating at conditions significantly hotter than the center of our own star.
Incredible. But the 17 minutes, why is that the game changer? Isn't it just, longer than before?
It's much more than just a longer time. This sets a world record for what's called long pulse operation, and that demonstrates the feasibility of steady-state operations. That's the crucial part.
Steady state, meaning continuous.
Getting towards continuous, yes. For fusion to be a practical power source, you can't just have brief flashes of energy, you need sustained reactions. Think of it like this. Getting a fire lit is one thing, but keeping it burning steadily for a long time is another challenge entirely.
Right. Needs control, fuel, stability.
Precisely. Holding plasma stable at 180 million degrees for 17 minutes proves that the complex control systems, the heat management, the magnetic confinement, they actually work for extended periods.
Yeah.
It validates the whole approach for future power plants.
So it wasn't just about hitting the temperature, but holding it there reliably.
Exactly. And they did this while maintaining what's called steady-state H-mode plasma. H-mode, or high confinement mode, is a state where the plasma holds onto its heat and density much better, more efficient fusion.
Okay.
Achieving steady-state H-mode for that long, well, it's a massive validation. It shows sustained, controlled fusion burn is possible, not just theoretically, but practically, paving the way for reactors that could actually run continuously.
That really does feel like a qualitative leap then, moving from short bursts to something resembling a continuous process.
It's a huge step in demonstrating the fundamental viability.
So what does this all mean for us, for the bigger energy picture? We hear about China investing massively. Figures like $1 trillion USD get thrown around for East. That signals huge strategic importance.
It absolutely does, and the implications are potentially enormous. Fusion energy, as we've said, promises almost limitless power.
From China?
What fuel again? Primarily isotopes of hydrogen deuterium, which is abundant in seawater, and tritium, which can be bred from lithium. So the fuel is plentiful.
And clean.
And fundamentally clean. No greenhouse gas emissions, no long-lived radioactive waste like fission reactors. That's the appeal. It directly tackles climate change and resource worries.
So East's success makes that vision seem closer.
It makes the engineering pathway seem more credible. Demonstrating sustained operation means we're closer to designing reactors that could provide a constant, reliable supply of clean energy. Baseload power, but clean.
Right. If we connect this to the bigger picture, this isn't just a lab success, it's potentially reshaping the whole global energy game.
It could be a catalyst, yes. A potential catalyst for a global shift away from fossil fuels. It could genuinely revolutionize the energy landscape if, and it's still a significant if, we can overcome the remaining hurdles.
What are those main hurdles now?
Oh, there are many. Engineering is huge. We need materials that can withstand the intense neutron bombardment inside a working reactor for years. We need efficient ways to extract the heat energy and convert it to electricity. And crucially, we need to make it economically competitive.
Right, it has to be affordable energy eventually.
Exactly. That trillion-dollar figure, whether precise or not, reflects the scale of investment needed, not just by China, but globally. Think of ITER in France.
Like international project.
Yes, the massive international collaboration, 35 nations working together. Our source material rightly points out that this kind of global cooperation has been vital and will continue to be essential. Fusion is too big, too complex for one nation alone, really.
So it's science, engineering, economics, and international politics all wrapped up together.
Absolutely. It touches on energy security, climate goals, technological leadership. It's all in there.
That really broadens the perspective. It's far more than just hot plasma in a donut. This raises an important question, though. We have this incredible scientific leap, but where do we realistically go from here to actually powering cities?
That's the multi-billion-dollar question, isn't it? It's vital to keep perspective. East's record is phenomenal, a major milestone, but we still need substantial R&D to get from experimental reactors like East or ITER to actual commercial power plants.
So still years away.
Decades. Likely decades before fusion power is widespread, yes. But breakthroughs like this shorten the perceived timeline. They build confidence, they attract more investment, and they prove the fundamental physics and engineering concepts are sound. The long-term vision, clean, safe, abundant energy remains the driving force.
It's a compelling vision.
It really is. So maybe a provocative thought for you listening. Given the huge costs and the global nature of this challenge, how critical will international collaboration versus national competition be in the next phase? And what kind of currently unforeseen scientific or engineering leaps might still be needed to make fusion power an everyday reality?
That's a great question to ponder. We've really only scratched the surface today of what this artificial sun achievement could signify. It's a reminder of human ingenuity, honestly.
Definitely.
We really hope this deep dive encourages you to keep exploring, keep asking those questions. The journey towards harnessing star power on Earth is definitely not over.
Far from it.
But milestones like East certainly make that energy future feel a little bit closer, a bit brighter. So keep those intellectual fires burning. For more fascinating deep dives like this one, please make sure you're subscribed. Maybe share this with someone curious about where our energy might come from next.
We appreciate you tuning in.
We absolutely do. We'll be here next time, ready to unpack another stack of sources for you.